Hi, I'm Thomas and I will present the Haptic Fidelity Framework, defining the factors of realistic haptic feedback for virtual reality. Providing haptic feedback in virtual reality has become a strong focus of researchers and designers to make the experience more realistic and engaging. As a result, a great variety of different haptic feedback devices have been proposed. Some of them you can see here. They differ greatly in their technologies, feedback possibilities, and overall realism, making it challenging to compare different systems. Current frameworks and evaluation methods only cover certain types of feedback devices or solely focus on the user experience. Together with domain experts, we developed the Haptic Fidelity Framework to analyze, compare, and understand the whole spectrum of feedback devices. The framework provides the means to assess haptic feedback devices in two dimensions: haptic fidelity and versatility. The haptic fidelity dimension provides the means to assess how realistic or abstract the feedback potential is. Generally, all types of feedback devices have a software calculating the feedback to control an output device that acts on the human body and creates sensory stimuli. We use these steps to structure 14 individual factors, which allow for detailed assessment of the perceptual and technological aspects. While a particular system might be able to provide realistic feedback for playing tennis virtually, the same device might not be suited to give realistic feedback for lifting a box. Therefore, each factor offers a qualitative assessment in the context of a specific use case. The individual factors are further separated into foundational and limiting factors. Foundational factors describe the features of a system and the value they provide, while limiting factors have the negative impact on the perception and diminish this value. In the sensing category, 5 foundational and 2 limiting factors describe the potential to create realistic or abstract haptic perception. The body location factor, for example, describes the degree to which the same locations on the body of the user are involved as in the intended use case. For realistic feedback of virtual tennis, the fingers and hands have to be involved where the racket is held, but also the arms and chest have to receive feedback for the forces of the moving rack and hitting the ball. The magnitude factor describes the degree to which the same intensity and variation of a stimuli are involved. The factor combines various physical measures such as forces, temperature, vibration, but also variation in texture. For example, when lifting a virtual box, the match of weight and texture variation should be assessed. The hardware category includes 5 factors. The degree of freedom factor assesses if the system can provide the same degrees of freedom. Feedback for objects that can be freely moved and rotated should provide 6 degrees of freedom, while slide doors would only need 1 and walls none. An example of a limiting factors are side effects, which describe the impact of unintended haptic stimuli created by the hardware. This can include vibrations or forces of moving parts or unpleasant traction from electric muscle stimulation. The last category, software, includes software precision, which describes the detail to which the software can simulate the intended haptic feedback. Here, the accuracy of an underlying software simulation or simply the detail of a mesh that is used as a collider is assessed. The software latency considers the impact latency has on the haptic perception. While most software for collision detection today does not impose a noticeable latency, a more complex simulation of softness might create a distracting delay. In our paper, we provide extensive examples on how to apply the framework and assess all factors. We also provide an approach to formalize these assessments in a score to allow for intuitive comparison. Versatility is the second dimension of the framework. It allows to assess how specific or generic a system's feedback is for a particular use case. This dimension covers the trade-off between highly realistic but application-specific and more abstract but widely applicable feedback. To assess how specific the feedback is, we provide a single factor with 5 levels of specificity. These range from being specific for one particular variation of use case, like in the example of the virtual climbing wall, where feedback for only this particular wall can be provided, over being specific for a group of use cases, like all small handheld objects, as in the device in the middle, to being completely generic in its feedback, as the vibration of most standard VR controllers. We intend our framework to provide researchers and designers of haptic feedback systems with the means to anticipate the realism and versatility of feedback, hypothesize evaluation results, compare different devices or variations, decide which devices to select for their use case, and finally, create a deeper understanding of haptic feedback. To be of practical use, We validate our framework by comparing the scores of haptic fidelity to the perceived realism of feedback. To cover a wide variety of different feedback systems, we did a literature review and identified 38 papers that evaluated perceived realism, and the haptic feedback was the only changing variable between conditions. We then assessed all 154 conditions of these papers with a framework based on the device descriptions and accompanying videos. We also calculated the effect size between all conditions of each paper based on the reported statistics. We then calculated the correlation between the effect size and the difference in haptic fidelity scores. We found a strong correlation between haptic fidelity and perceived feedback realism. This indicates that this dimension accurately describes the potential of a system to create realistic haptic feedback for users. In a second analysis, we also calculated the correlation between the haptic fidelity and versatility and found a strong negative correlation, which confirms that most current feedback systems exhibit the trade-off between highly realistic but application-specific and more abstract but widely applicable feedback. We hope that our framework gives researchers and designers a structured approach to assess and compare the whole variety of haptic feedback devices. In this talk, we were only able to give a rough overview of the framework and encourage you to have a deeper look at our paper for more details.